The moment a user clicks a button in a modern web app, a payload of data begins an organized journey through distinct layers of code. We are tracing this journey through a production-ready expense tracking system using a split interface that pairs a control panel for inputs with an active data table. Behind this surface layer, 3 separate systems coordinate through strict protocols to maintain the integrity of every transaction. Our objective is to track a single data payload. We will follow user input from this surface layer down to permanent database storage and back up into a shaped visual analytics dashboard. Mastery of this end-to-end traversal differentiates basic scripts from resilient, enterprise-grade software engineering. This architecture relies on 3 pillars. The Streamlit frontend acts as the reactive interface, capturing user intent. The FastAPI server acts as the central brain, managing validation and logic. Finally, the MySQL database operates as persistent storage, writing records to disk. These components interact through a rigid contract. The frontend cannot access the database directly. It communicates with the server only through standard REST API calls. This separation of concerns ensures that front-end updates or errors never compromise the underlying data schemas. The trace begins by initiating a new expense entry. The user populates the date, amount, and category fields within the Streamlit UI and submits the form. Before this data can reach the database, it must pass the FastAPI REST boundary. The backend uses Pydantic schemas to enforce a strict data contract. These schemas dissect the incoming JSON, verifying the exact data types for the date, amount, and category. This includes boundary rules, such as rejecting the payload if the user submits a negative monetary amount. Only perfectly validated data is handed off to the internal database module to execute the creation step. To safely interact with MySQL, the backend utilizes a context manager. This opens the database connection and ensures the cursor closes immediately after the operation. The system then executes the SQL insert query, committing the transaction and writing the record to the disk. Because database operations can fail, these functions are wrapped in try-except blocks to intercept execution errors. If a database error occurs, the server converts it into a generic HTTP 500 exception before responding to the frontend, shielding the internal system structure from the user. This rigid API contract guarantees that the database is never polluted by malformed or invalid inputs. We now shift the trace from writing data to reading the complex aggregations required for the dashboard view. The dashboard requires categorized breakdowns, spend percentages, and month-over-month comparisons. Querying raw data and forcing the front end to perform these calculations on the fly would significantly degrade the user experience. In this system, all data shaping and aggregation occurs securely on the back end. The server handles the logic for calculating deltas and manages edge cases, such as preventing errors when comparing against a month with 0 spending. The server packages these metrics into the Analytics Dashboard payload, a data structure mapped to the front-end charts. The Streamlit charts and pandas tables, like this line showing a drop from 5,222 to 4,790 rupees, simply ingest pre-computed metrics without heavy math. Offloading analytical processing to the backend allows the interface to focus entirely on responsive rendering. Returning to the interface, we can see how the UI manages state during a user interaction, such as selecting a row in the data table. Streamlit follows a top-to-bottom execution model. Every user click causes the entire Python script to rerun from the first line. When a user selects a row, the script captures the row index and immediately restarts the execution cycle. During this rerun, the script uses the captured index to populate the left-hand form, transitioning the UI into update mode. This constant resetting poses a problem. The UI must find a way to remember a success message after the script reloads. The system uses session state to store transient memory across these forced reruns. Once the API confirms success, the app writes a message to the session state and triggers a rerun. The script then reads that message, renders the success banner, and deletes the key to prevent the message from lingering. Engineering a reactive interface in this environment requires deliberate memory management to maintain the seamless experience of a single-page application. Diagnosing a failure across a decoupled stack is difficult without a clear path of evidence. The system uses a centralized logging architecture that routes events from both the front end and back end into a single shared log file. The front end log user intent, recording exactly when an analytical breakdown is requested. We can then trace the corresponding API call on the server, verifying that the request reached the correct endpoint. Finally, the database functions log their results. If an error occurs, the full Python traceback is preserved here to isolate the cause. This unified chronological record turns fragmented events into a coherent narrative of the system's health. System integrity is verified by PyTest integration tests. These operate on real SQL queries rather than mock data to confirm the database interactions remain valid. This trace confirms a verified lifecycle: user intent, strict API contracts, backend data shaping, and unified observability. The resilience of a production system rests on the integrity of the data contracts and observability pipelines that bind its layers together.